This is the second problem, 5.56, and for this problem we have 8 circuits to solve. So I will show you the methodology to solve like groups of problems. So this first methodology will solve A, B, C. Then we'll have a second methodology that solves D and E, another one for F and G, and the last one for H. Okay. So in this problem, it's given, so all these circuits, they have NMOS, in MOSFETs, so transistor NMOS, and the threshold voltage is 0.8 volts. We are not considering the channel modulation effect, and the device transconductance, Kn, is 0.5 milliamperes per square volts. And so in this ABC, the only thing that is changing is basically the unknown here is V1, V2, and V3, but the parameter that is changing in this circuit is this current source here. So it goes from 10 microamps to 100 microamps, and then in C 1 milliamps. But the methodology is always the same. Okay. So how do we solve this problem? So first thing is that we can consider that the NMOS is operating in the saturation region, and then for the saturation region we know that the current ID is equals to 1/2 of the device transconductance times the overdrive voltage squared, right? So if we look at this circuit here first, here is the drain, here is the source, here is the gate. So we know that the gate's voltage is 0. We know that the drain voltage is 5 volts, right? Because it's shorted here, and here it's connected to the 5 volts here, and it's grounded here. So we can calculate ID. We can actually estimate the overdrive voltage, right? Because one thing is that this current source here, 10 microamps, forces the current ID to be 10 microamps, right? Because the current that's flowing here at the source is the same current that's flowing up here in the drain. So our ID is actually 10 microamps. And from that we can calculate, so the process transconductance, 0.5 milliamperes, we can calculate the overdrive voltage. And basically the overdrive voltage is equals to square root of 2 times 10 microamperes divided by the device transconductance, which is 0.5 milliamperes per square volts. And this gives us an overdrive voltage of 0.2 volts. Okay, so just remember that this voltage source here, right, this one here, it forces this current that's flowing up here, okay, and down here to be those 10 microamps. And those currents, here is ID, here is IS, but as we know, for the MOSFET, basically ID is equal to IS, okay? So we got the overdrive voltage. Now with the overdrive voltage, we can calculate the source. We can calculate the voltage at the source, which in our case is actually V1. So if we go down here, right, this V1 is equals to Vs, right, because it's the voltage at the source terminal here. Now we know for an NMOS that the VGS is equals to the threshold voltage plus the overdrive voltage. Now this is the same as Vg minus Vs, and that's equals to Vt plus the overdrive voltage. And remember that right here Vg is equals to 0 volts because it's grounded, right? So Vs is equals to minus the threshold voltage plus the overdrive voltage. And in our case, Vs is equals to 0.8, so minus 0.8, because that's the threshold voltage, plus the overdrive voltage that we just calculated. So Vs is equals to minus 1. And we know that V1 is equals to Vs, so V1 is equals to minus 1. And that's the results for part A. Now part B and C, it's just the same thing. You just have to change this value here. So I won't solve it here to not make the video so long. Okay, but it's just like a matter of changing this current here. Okay, so let's go for D. And D and E, they are basically the same thing too. We just have to change this current here. Okay, so for D now we have this topology here where the gate is connected to the drain. So if we look here, we have the drain, here we have the gate, right, and here we have the source. So the gate here is connected to the drain via this wire here, right? So one thing is that we know that VD is equals to VG, and in this case is equals to V4, right? The unknown here in this circuit. So that's what we want to define. And again, we can assume saturation condition. So at the end of this part here, I will verify the saturation conditions. I didn't do it for the first one, but you can verify. I just following the same steps, so I remember to do it in this one here. So if we assume saturation operation of the MOSFET, so we have that the drain current is equals to half of the device transconductance times the overdrive voltage squared. And because we know that so let me just verify something here. Because we know that, so one thing is that there's no current flowing here, right? Because the current at the gate is 0, so Ig is equals to 0 amperes, right? So this 10 microamps here is actually the current that's flowing here at the drain, right? So we know ID. And if we isolate again V overdrive in this equation is the same as the square root of 2 times ID divided by the device transconductance. And this gives us an overdrive voltage of square root of 2 times 10 microamps divided by the process transconductance, that in our case the device transconductance, sorry, is 0.5 milliamperes per square volts. And this gives us an overdrive voltage again of 0.2 volts. Okay. Now if this overdrive voltage, we know that the overdrive voltage is equals to VGS minus VT. Same equation that we used before. And this gives us that V overdrive is equals to Vg. Now let's look at the circuit again. VGS, so is Vg minus Vs minus the threshold voltage. Now if we look at the circuit right here, this source is grounded. So we know that Vs is equals to 0 volts. This one here, which gives us the gate voltage. So the voltage at the gate is equals to V overdrive plus the threshold voltage. So Vg is equals to 0.2 plus the threshold voltage, that's 0.8. Okay, it's given by the problem. So Vg is equals to 1 volt. Now because Vg here, so let me draw with another color. So Vg here is the same as Vd, that's the same as V4, right? Because it's the same node. We know that V4 is equals to Vg, in this case is 1 volts. Now, because we assumed saturation condition, we have to verify two conditions, right? The first one is that VDS should be greater than the V overdrive, right? So if it's equals or greater than that, it operates in the saturation region. And this gives us VD minus VS, so we know that VD is V4, so it's 1 greater or equals to V overdrive, which is 0.2. So this first condition here is satisfied. And the second condition is that VGS should be greater than the threshold voltage. And again, because VGS, the voltage at the source is 0 volts, we just have to verify if VG is greater than VT. And actually, again, because it's shorted up here, VG is actually V4, so 1 is greater than 0.8. So both conditions are satisfied, and this assumption of saturation condition that allow us to use this equation here, okay, it's valid, okay? So let's go for F and G. Now for F and G, we have this circuit here. And this problem is it's a little bit tricky if you don't assume that it's similar to the previous ones. So I will show you how to solve, and basically we have to find out quadratic equation to find out the drain voltage. So let's get started. So for this particular problem, we know that Vg is equals to, so we know that Vg is equals to Vd, which is equals to V6, right? Because if you look at the circuit, here's the drain, here's the source, here's the gate. Now this path here gives us that the voltage at the gate is the same as the voltage at the drain, and because we are calling this potential here at this particular node equals to V6, they are all equal, right? They are all the same potential. And down here we have that the voltage source, so the voltage, the potential at the source is equals to 0 volts because it's grounded. So that's another information that we get from the circuit, right? Now to calculate ID, so if suppose we are calculating ID, it's basically, we can calculate using this Ohm's law over here. So this current here, that's ID. And why it's ID? Because there's no current flowing here at the gate. So this current here that's flowing through this resistor, right, is the same that's flowing here at the drain. So that's the reason we can assume ID as the same current that's flowing through that 400k ohm. So in this case, ID is 5 minus VD. So I'll call VD here. It could be VD, VG, or V6, but I will use VD. Okay, divided by the resistance. So it's 400k ohms. And that's the equation that we have for ID. Now remember that ID is equals to 1/2 the device transconductance times the overdrive voltage squared. And in this case, ID is 5 minus VD, right? We are just substituting this one here for ID, divided by 400k, and that's equals to half the process transconductance. So we have 0.5 milli, it's not the process, it's the device, right? Process is prime, so here we are already multiplying by the aspect ratio, so it's milliamps per square volts. And the overdrive voltage is VDS, okay, minus the threshold voltage squared. Okay, now if we look at this particular term here, we know that VDS is equals to VD minus VS. Now if we remember here in the circuit, Vs is equals to 0 volts. So in this case, VDS is actually equals to VD. And now we have a single equation with a single unknown, because this term here, it becomes just VD. So if we rearrange this equation here, we then get that 5 minus VD divided by 400k, 1 over half times 0.5, which is also half milliamperes per square volts, times VD minus VT squared. Okay, and if we rearrange this equation here, there are ways to, like, we can multiply both sides by 400k, and then we can rearrange VD. Now remember, this one here, it's a square, so it gives us VD squared minus 2 VD times VT plus VT squared. So if we rearrange this entire thing here, we get something that is 200 VD squared minus 318 VD plus 180, and that equals to 0. So we could divide everything by 2 here, so to get, like, to simplify the circuit, or divide everything by 118 to get like a simplified version of this equation, right? But the thing is that if you use those coefficients here in the quadratic formula, you can calculate the value of VD, right? So in this case, our VD is equals to, so if we take this coefficient here, so we'll call B, this one C, this one A, right? So for the quadratic formula, we have that minus B, so it's 318 here, plus or minus square root of B squared, so it's 380 squared, minus 4 times A times C, so it gives us minus 4 times A, which is 200, times C, which is 180, divided by 2 times A, so it's 2 times 200. Okay, if we solve this quadratic equation here, so we get two answers. Okay, so I'll call VD1, that is 1 volts, and VD2, that is 0.59 volts. Now, which one do we pick? 1 volt or 0.59 volts? The thing is that if we use 0.59 volts for VD, remember that VG is actually equals to VD, and this gives us a VGS that is less than VT, right? Because remember here, so this voltage at the gate is the same as the voltage at the drain. So if we pick VD2 equals to 0.59, that's VG also, right? And remember that so here's the source, here's the drain, here's the gate. Now the voltage at the source is 0. So this VGS term here gives us VG minus 0 should be greater than VT. And it actually gives us that 0.59 is less than 0.8. And because of this condition here, it basically tells us that the MOSFET is not operating in the saturation region, right? It's actually cut off. So if we pick 0.59, this equation here that we use for ID, this one here, it doesn't hold, so it's not valid. Now, if we pick this one here, VD equals to 1 volts, then we get that 1 volts is actually greater than VT, right? And this one here agrees with our assumption of saturation operation, okay? So we pick, in this case, VD equals to 1 volt. And because we have VD equals to VG equals to V6, that's basically 1 volt. So that's the answer. And if you want to calculate ID, in this case, ID, if we go up here, we know that ID is equals to 5 minus VD divided by 400K, right? It's just, here's ID. So it's 5 minus VD, which is 1 divided by 400K, which gives us 4 divided by 400K. In this case, ID is equals to 10 microamperes. Now, the first condition here, VGS greater than VT, is satisfied. So let's just verify the second condition, that is VDS, that should be greater than V overdrive, right? So let's see what's the V. Did we calculate V overdrive? No, we can calculate V overdrive. So VDS is just 1 volt, so should be greater than the overdrive voltage. And now the overdrive voltage, we know that's VDS minus VT. So this gives us 1 greater than VDS is just VD, right? Because this source voltage, the potential at the source is 0. So VD is 1 minus the threshold voltage, which is 0.8, and this gives us 1 greater than 0.2. So it agrees with the assumption of saturation operation of the MOSFET. Okay, so that's what we have for F. And if we look at G, it's just the same. Let me see. Yeah, it's just the same thing, but we are changing the value of this resistor here. Okay, but the analysis is just the same. So you can use the same methodology that I just showed you. Now the last problem. So H, we have this circuit here. Okay, and from this circuit, there's some things that we can gather, some information that we can gather from this circuit. So first thing is that this is the drain, this is the source, this is the gate. So if we look here at the gate, right, it's grounded. So VG is equals to 0 volts. Now if we look up here, the drain is actually connected directly to this 5 volts voltage source. So VD is equals to 5 volts. And we also know that because we are defining V8 as the voltage, the potential at the source, we know that V8 is equals to the source voltage. Okay. Now, one thing is that we know that for MOSFETs that the current at the drain is equals to the current at the source. Okay, so we can calculate the current at the source using Ohm's law here. So we know that the current at the source is equals to V8 minus 5. Sorry, let me rewrite this one here. Minus 5. So is this potential here minus this potential here. So V8 minus 5 divided by 400 k ohms. So that's the equation for IS, that is equals to ID. Okay, now we can assume saturation operation of this MOSFET again, and then we can use the equation for the current ID equals to half device transconductance times the overdrive voltage squared. Okay, so if we substitute this equation here, we get that V8, and one thing here is that remember that V8 is equals to Vs. So we can substitute V8 here as Vs, and then Vs plus 5 divided by 400 is equals to 1/2 times 0.5 milliamperes per volt squared times the overdrive voltage. And what's the overdrive voltage in this case? It's VGS, right, minus VT squared. Okay, and because the gate potential is 0, this equation becomes Vs plus 5 divided by 400k equals to, I will multiply those two here already, so milliamperes per square volts. This gives us minus Vs minus Vt, okay? Because Vgs is equals to Vg minus Vs, and this one here is 0. Okay, so that's why we have VGS here, just minus Vs here, and that's squared. And again, if you look at this formula, we have a single unknown, right? Vs here and there. So we can expand this thing here, and if we expand and multiply by 400k here, and then isolate the Vs squared, Vs, and the constant term, and equate that equals to 0, we get an equation that is 100 Vs squared plus 159 Vs plus 59 equals to 0. So that's the quadratic equation that we have. Here is A, here is B, here is C. So we can solve for Vs, and Vs is going to be equals to minus B, so minus 159 plus or minus square root of, I'll put 159 squared, right, minus 4 times A, which is 100, times C, which is 59, everything divided by 2 times 100. And if we solve this one here, we get Vs1 and Vs2. And Vs1 is minus 1 volts, and Vs2 is minus 0.59 volts. And again, if we pick this one here for Vs, we have to remember that Vgs should be greater than Vt. And because Vg is equals to 0, so minus Vs should be greater than Vt. And if we substitute minus 0.59 here, we get 0.59 greater than 0.8, and that's not true. So we have to pick this one here, because this one gives us minus 1 greater than 0.8, and this is 1 greater than 0.8, and that's okay. So this first condition here for saturation operation, it holds if we pick Vs1 equals to minus 1. And because Vs1 is actually, so if we go down here, let me show you here. So this potential here is Vs, right? And Vs is equals to V8. Basically our result is that V8, which is the unknown in this circuit, is actually equals to Vs, which in our case is equals to Vs1, right? And that is minus 1 volts. So let's just verify the second condition for saturation mode operation, okay? And that condition is that we should have, let me verify it again, VDS should be greater than the overdrive voltage. So VDS should be greater than the overdrive voltage. Now what's the value of the overdrive voltage? We can calculate it here. So we have VD minus Vs greater than VGS minus Vt. So VD we know that is 5, right? It's connected directly here. So it's 5 minus Vs, which is V8, so minus 1, should be greater than VGS, so Vg is equals to 0. Okay, so this gives us 6 greater than this one is 0, minus Vs is 1, minus 0.8 from the threshold voltage given by the problem. So indeed 6 is 6 is greater than 0.2. So both conditions for saturation mode operation hold, and that's the result, right, V8. And because both conditions they hold, this equation here that we use for ID, right, this one here, it's correct. So we can actually use this equation to solve the problem. Okay, so that's it for this particular problem.